How are you all doing this morning? Good deal. So today we are going to be talking about complex power, but before we do that, I want to talk about the concept of effective and RMS values. If my pen will write, there we go. So when we were covering DC analysis, we found that for a given resistor R, the average power delivered to that resistor was simply V squared divided by R, or I squared multiplied by R. When we looked at AC circuits, we found that the average power delivered to a given resistor was 1/2 Vm squared over R, or 1/2 Im squared times R, where Vm and Im denote the magnitude of the sinusoidally varying signals. So what we're going to develop over the next several minutes is a means by which to relate these two quantities. And what I mean by that specifically is we're going to take an alternative look at our AC signals and figure out an electrical equivalent DC signal that supplies the exact same amount of power to our given load. The reason that we're going to do that is because carrying around all of that instantaneous power information, you guys have noticed if you tried to do any of those calculations or worked on any of the homework problems. So starting from today, we are really going to be looking at all of our power quantities from effectively an average perspective, okay? So I'm about to draw a picture here. I'm going to try to make it not terrible, but you all have seen me try to draw things before, so. So what I'm attempting to draw here is a receptacle that you might see in your home, maybe potentially on a wall near you, that distributes power here in the United States. Receptacle is going to look something like this. It's going to have a long prong, a shorter prong, and then typically kind of a half circular shaped prong. This guy here is our ground prong. This guy here is what we would call our hot wire prong. And this guy here is what we would consider our neutral wire prong. So here in the States, can anybody tell me what the voltage between the hot wire and the neutral wire is?
Shouldn't it be 120?
All right. So $120 volts. So you're both right and wrong. And this is where the concept of effective values comes in, okay? So the 120 volts that you're familiar with being supplied by a receptacle in an American home is actually what's called an RMS quantity, okay? And we'll talk a little bit more about what that means in a minute. Power is distributed in the United States by AC systems, right? So it's actually a three-phase AC system, but we are not ready to discuss what a three-phase system really means. But in our home, we're only looking at a single phase of it. So that 120 volts RMS is really a shorthand notation for $169.706 cosine 120 pi t plus whatever phase angle our signal happens to have when we start looking at it, volts. So what that 120 volts RMS quantity really represents is the DC voltage that would supply the exact same amount of average power as this sinusoidal voltage. So this guy is what's called the effective value, the effective, and this guy here would be our sinusoidally varying time domain signal. So now let's talk about how we get to that 120 volts. Okay, we're going to do it in a generic standpoint first, and then we'll talk specifically about for a sinusoidal signal in a moment. So I have those two average power, or excuse me, I have that average power relationship at the top for a DC signal, right? So I know that what I'm going to call V effective squared divided by R is representative of the average power delivered to some resistor R for a DC signal. And I'm going to set that equal to the average power delivered to some resistor by a time varying periodic signal. So that would be this guy right here. So alternatively, because I don't want to make it seem like I just pulled that right-hand side of that equation out of thin air, we could express an effective current. So our average power given by a DC current would be 1 over T times the integral over 1 period of I squared T multiplied by R dt, which is the exact equation that I derived at the end of class yesterday that we used for those last couple of problems on, I think, homework set 22, I believe. Okay. So I can see that there is a common factor of 1 over R on both sides, so I can really throw that away. So what's interesting about that is it means that the value of the resistor that we are trying to deliver power to actually isn't even important in determining the effective value at all, which is going to make our life a little bit simpler. So I could say then that V effective squared is equal to 1 over T times the integral of the instantaneous power divided by the resistance, which is going to be V squared of T dt. And on this side, I can say that I effective squared is then just going to be 1 over T times the integral from 0 to T of I squared dt. And now all I'm going to do to figure out my DC equivalent that supplies the exact same amount of power as our sinusoidal signal is take the square root of both sides. So my effective value for my voltage becomes the square root of 1 over the period times the integral over 1 period of the square of my voltage signal. And similarly, the effective value of a sinusoidal or of a periodic current becomes 1 over t integral from 0 to t I squared t dt, like so. So we actually wind up taking the effective value of a voltage waveform and a current waveform using the exact same equation. So that's pretty handy as well. All right. So let's put this equation into use. So actually, before we do that, I want to talk about one other thing here. So up at the very top, I called these both effective and RMS values. The reason they are called RMS values is because we're taking the square root of the arithmetic mean of the square of the signal. So we're taking the square root of the average value of the square of the voltage and the square root of the average value of the square of the current. So that's where that RMS comes from. And we're going to use that RMS thing as a unit to differentiate between effective values and instantaneous values of voltage. All right, so let's say that I have the following time domain voltage signal. Start with something I think is pretty easy. This will be T measured in seconds. This will be our voltage measured in volts. And let's say that our signal looks something like this. It's 5 volts for some amount of time. And then it's 0 volts for an equal amount of time. And then 5 volts. And then 0 volts. And then 5 volts, like this. So we have a periodic signal. And let's say that it's changing state every 2 seconds, like so. The effective value of this periodic waveform can be determined by just using that simple equation that we have, right? So for this series of rectangular pulses, what is the period?
4 seconds.
4 seconds, thank you. So we're going to multiply times the integral. It's a piecewise function, so I'm going to split my integral into 2 parts. Over the time interval from 0 to 2 seconds, what's the value of my voltage?
5 volts.
All right, so I'm going to put 5 volts squared here. And then over my second time interval from 2 seconds to 4 seconds, what's the value of my voltage?
0 volts.
Square it. There we go. So evaluating this integral should be fairly trivial. Should be pretty obvious that that guy right there goes to 0 because we're integrating nothing over a period of time. So this is going to look like the square root of 1/4 of a second. Oops, don't know what the heck happened there. Scrolling without my desire. 1/4 of a second. Then we're going to have 25 volts squared. And then we have the integral from 0 to 2 seconds of dt, right? Since our voltage is a constant value, that's pretty easy. So this is going to look like the square root of 1/4 seconds times 25 volts squared times 2 seconds minus 0 seconds is going to be 5 divided by the square root of 2 volts RMS. So that is the DC equivalent voltage that supplies the exact same amount of power to an arbitrary resistance as that series of rectangular pulses. Okay, so we would say that the RMS value of that voltage waveform is 5/square root of 2 volts. Now let's look at a different waveform. And just for the sake of argument, we'll make this guy a current. So let's say that every 3 seconds, our current increases to a value of 10 amps and then drops down, creating what we would call a sawtooth wave. Like so. So this is another type of signal. The last signal that we dealt with was what would be called the square wave. Technically, it's a square wave with what's called a 50% duty cycle. So what that means is exactly half of the time the signal is on or has some non-zero value, and half of the time the signal is off, has some zero value. And if we look back here real quick, the effective or RMS value of our square wave with a 50% duty cycle is just the maximum value of the square wave divided by the square root of 2. So it has a very simple relationship that will be true for any square waves having a 50% duty cycle. We'll see that there's also going to be a similar relationship here with sawtooth waves, which again is another commonly used electrical signal that electrical engineers see pretty often. So our effective value for our current here, I effective, is going to be the square root of, what's our period? Somebody else.
6 seconds.
I just-
Or 3, sorry.
3 seconds. Yeah, 6 seconds would be 2 cycles.
Yeah.
And then we're going to integrate from 0 to 3 seconds our waveform. So this is simply a linearly increasing function. So I'm going to put in the y equals mx plus b format. So in this case, what's our slope?
10/3, so whatever
10
that is.
over 3 seconds. Yeah, so that's perfectly reasonable there. Times time. And then our y-intercept in this case is 0, so it's going to be plus 0, so I'm just going to leave that bit off. We square it like so. And so doing the math here, that's going to look like 1/3 seconds. That 10 amps per 3 seconds quantity squared can come out. It's a constant, right? So that's going to look like 100 amps squared over 9 seconds squared. Then we're going to have the integral from 0 to 3 seconds of t squared dt. And we perform the integration. So let's see, I'm just going to leave this as 1/3 seconds here. 100 amp squared over 9 seconds squared. So the integral of t squared is t cubed over 3, right?
Right.
We're going to evaluate that guy at 3 seconds and 0 seconds. So that's going to look like 1/3 seconds times 100 amps squared over 9 seconds squared times 1/3. And then I'm going to have, let's see, t cubed evaluated at 3 is going to look like 27 seconds cubed, right? And then when we evaluate it at t is equal to 0 seconds, that'll be minus 0 seconds cubed. And so this 3 seconds here multiplied by this 9 seconds here cancels out this 27 seconds cubed here, leaving us with 10 over the square root of 3 amps RMS. So it is not a coincidence that for our triangular wave, it's simply the maximum value of the function divided by the square root of 3. That is effectively our conversion factor from looking at a sawtooth wave and getting the effective value, simply the max value over root 3. Doesn't matter if it was, if it had a period of 4 seconds or 45 seconds, it'll always actually come out to be that. So now I would like to look at a sinusoidal function, okay? So let's say that our voltage V of t is Vm cosine omega t plus some phase angle theta v volts. Our effective value for our voltage would be the square root of 1/t integral from 0 to t of v squared t dt. So we're going to be filling in some of these blanks in a second. It may require a little bit of a review, mainly to figure out what the relationship for the period is, right? So if we have a sinusoidal signal, we're dealing with the cosine function here, and I am, just for the sake of argument, going to graphically here set our phase angle to 0. So we're going to start at this value, where this guy is Vm, and this amount of time is our period. Does anybody remember what relationship we have to omega here?
Omega would be equal to 2 pi over your period.
All right, so that means it's simply 2 pi over omega, right? All right, so with that in mind, one over t would be omega over 2 pi, and now we'll integrate from 0 to 2 pi over omega. And I'm going to use that trig identity that I used before when we multiplied cosine functions together. And what I'm going to wind up getting here is 1/2 Vm squared plus 1/2 Vm squared cosine twice omega t plus twice theta v. Close that off. This whole big ugly thing is under the square root sign. And now what I'm going to do is I'm going to break that integral up, much like we did when we were calculating the average power. So I'm going to have 0 to 2 pi over omega of 1/2 Vm squared dt plus the integral from 0 to 2 pi over omega of 1/2 Vm squared cosine twice omega t plus twice theta v dt. All of this is under the square root sign. So let's look at that sinusoidally varying part first. All right. I'm going to actually continue this guy on here real quick. I don't need to actually, now that I think about it. What I'm going to do instead, so this AC term here on the right-hand side is oscillating at twice the frequency. So again, assuming our phase angle is 0, it would look something like this. Over the exact same amount of time. So what happens when we integrate that new sinusoid, the twice frequency term, over exactly 2 periods? Anybody have any thoughts?
Could you repeat the question?
So we are integrating that curve that I've drawn in red, which is representative of cosine 2 omega t, over exactly 2 periods of its waveform. What should that integral result in? Another way to think about it is, let's say that we're integrating a cosine function over exactly 1 period. It stands to reason that if we integrated it over exactly 2 periods, it would just be twice the result of integrating over 1 period. So what's the cosine? What's the integral of cosine over exactly 1 period? You guys told me the answer to this, no problem, like 2 days ago or whatever. So what I'm asking for is this area plus this area.
It would just be 0. Yeah.
Exactly right. It'll just be 0 because I have all this area above the horizontal axis being exactly canceled out by all of this area below the horizontal axis. So whenever I integrate a sinusoidal function over an integer number of periods, the answer is always going to be 0. So all we have left is that DC portion. The effective value of that is pretty trivial to find. We're going to have omega over 2 pi times 1/2 Vm squared times the integral from 0 to 2 pi over omega of dt, which is just going to be the square root of omega over 2 pi times 1/2 Vm squared times 2 pi over omega minus 0 is going to look like Vm divided by square root of 2. So for a sinusoidal signal, in this case, we did a voltage, but it should be obvious that the result will be the exact same if our signal happens to be a current. For a sinusoidal signal, the effective value is simply the magnitude of the sinusoid divided by the square root of 2. What's really interesting about this is that this result does not depend on frequency, and it does not depend on phase angle in any way, shape, or form. So all sinusoidal signals, whether they're in the United States and operating at a linear frequency of 60 hertz, having voltages anywhere from 120 to 480 volts RMS, to Europe, where they use 230 volts RMS at a frequency of 50 hertz, they're all just the time domain magnitude divided by the square root of 2. Okay, so that, sorry, what the heck just happened? Leads me to our next topic, which is complex power. All right. So for a generic load impedance Z, in the time domain, we have some voltage Vt across it. We found, and let's say that V of t explicitly is Vm cosine omega t plus theta v volts. I of t was Im cosine omega t plus theta I amps. We found that the average power delivered to this generic impedance was 1/2 Vm Im cosine theta v minus theta I. We can split that P average quantity as Vm over the square root of 2 times Im over the square root of 2 cosine theta v minus theta I, or more simply, V effective, I effective cosine theta v minus theta I. So at the very least, what using the effective value does is gets rid of that factor of 1/2 that we were having to carry around, right? So for a resistor, the average power would just be V effective times I effective, or V effective squared over R, or I effective squared times R. It gets us exactly back to our simple DC relationships for average power, okay? Now, people much smarter than I am recognized that this relationship here is simply the real part of the following operation. 1/2 voltage phasor times the complex conjugate of the current phasor is the real part of what I'm going to call the RMS phasor voltage, denoted by this tilde over the V, times the complex conjugate of the RMS phasor current. So you might be a little bit confused here, perfectly reasonable. So I'd like to kind of spell things out again about how we convert from the time domain all the way through this chain. All right. So in the time domain, we may have a voltage V of t is equal to Vm cosine omega t plus theta v, and current Im cosine omega t plus theta I. In the frequency domain, this looks like V phasor is equal to Vm angle theta v, and I phasor is equal to Im angle theta I. And then finally over here, in what I'm going to call the RMS phasor domain, I could say that V RMS phasor is simply Vm divided by the square root of 2 angle theta v, and sorry, I RMS phasor is equal to Im over the square root of 2 angle theta I. Okay, so that's how we're converting from the time domain to the frequency domain, and then finally to the RMS phasor domain, where we'll be working for the next several days. So that operation that we did a moment ago, complex, let's see here, it's called the complex power. It has a symbol S with a bar over it because it is a complex number. And it is defined to be 1/2 voltage phasor times the complex conjugate of the current phasor, or simply the RMS voltage phasor times the complex conjugate of the RMS current phasor. Complex power is a quantity that is used by power engineers to succinctly characterize the power absorbed by a given load in a sinusoidal steady state circuit. It is actually an incredibly powerful quantity in this type of analysis because it contains all of the information pertaining to the power absorbed by a given load. And I'll explain what I mean by that momentarily. So before we go into the different parts of complex power, I'd like to talk about the units, because this is something that can potentially be confusing to you all. So complex power is defined as the product of a phasor voltage and a phasor current. So what do you guys think the units should be?
Would it be watts?
Watts. That is a perfectly reasonable assumption based on everything that you've learned to this point. However, to avoid confusion, we call the units of complex power what are called volt amperes. So dimensionally, they are the exact same thing as a watt, but we use volt amperes because watts are used for average power. And we don't want to confuse when we're talking about, a power engineer doesn't want to confuse talking about average power versus talking about complex power, okay? So complex power is measured in volt amperes. Now, our complex power is inherently a complex number. So if I substitute in our RMS phasor domain, actually, let me take one more step here to be clear what I'm about to do. VM over square root of 2, I'm going to now call VRMS or V effective because it's the effective value of our voltage, angle theta V. And similarly, I can say that IM over the square root of 2 is IRMS, angle theta I. So if I substitute in those relationships, I can express my complex power in a couple of different ways, all right? So I could say that S in rectangular form would be VRMS times IRMS cosine theta V minus theta I plus J VRMS IRMS sine theta V minus theta I. Or in polar form, I could say that it's simply VRMS IRMS angle theta V minus theta I. And all of these different representations, both the polar form representation and the rectangular form representation, have different names. So we're going to start by looking, revisiting average power, okay? So average power is simply the real portion of our complex power given by VRMS IRMS cosine theta V minus theta I, which we know to also be, I'm going to do this in a different color, 1/2 VM IM cosine theta V minus theta I. I'm writing it out in this way in blue here to remind you all that we are literally talking about the exact same average power that we have previously discussed. It is literally nothing different than what we have already covered. We're just getting to that result in a slightly different way, okay? The average power represents, sorry, lost my place here. The average power represents the portion of the complex power that is capable of performing work at the load, and it is measured in watts, okay? So our standard power relationship there, or power unit of watt, okay? So the average power is the portion of the complex power that is capable of performing mechanical work. Our next thing that we're going to talk about is what's called reactive power. Reactive power is the imaginary portion of our complex power. So it is given by VRMS IRMS sine theta V minus theta I, okay? You might see it denoted as Q, right? So actually, let me give myself a little room here. Average power, we have been using the letter capital P. We're going to continue to do that. I may write it as P with an AVG under it. I might forget to do the AVG, but capital P is related to average power. Q is the reactive power. This is, again, a product of voltage and current, so it seems like the units would be watts. To make things less confusing, we use the units VAR, volt amperes reactive, okay? So if you ever hear somebody talking about this load absorbs so many VARs, they're talking only about the reactive power portion, okay? The reactive power represents the portion of the complex power that continuously flows back and forth between the source and the load in a steady state sinusoidal system due to the presence of capacitors and inductors. So when we were talking about the instantaneous power, I guess it might have been yesterday actually, or maybe it was the day before that, I can't quite remember. We saw that the average power absorbed by a capacitor and the average power absorbed by an inductor was 0. We observed that exactly half of the time a capacitor and an inductor absorbs power, and exactly half of the time the capacitor and inductor supplies power back to the source, okay? So the reactive power represents that portion of the complex power. Pretty common question that students have asked me says that if reactive power just represents power being transferred back and forth in a system, what is it actually used for? Okay. Reactive power is energy storage, temporary energy storage in an electrical grid. So what I mean by that is on any given day, there is a certain amount of power that a portion of the grid will consume, okay? But so let's say that on an average Sunday, the city of Ruston absorbs, let's call it 50 megavolt amperes of power. That's probably a large overestimation, but for what we're talking about, it won't really matter. Okay, that's what happens on an average Sunday. What do you think happens to that level on, say, Super Bowl Sunday?
It would probably like at least double.
Yeah, it's so at certain times of the year, we'll see that there's a lot more stress on our electricity grid. It wouldn't make sense for us to invest the money in designing the entire grid to handle those peak power conditions all throughout the year when we know we're only going to experience them maybe once or twice a year on big days like that, like the 4th of July, people might be outside barbecuing and grilling and all that kind of stuff. But Super Bowl Sunday, usually early February, it's still cold. So you've got, your TV going, your heater going, you got a lot of people at your house, all, consuming electricity and stuff like that. So the reactive power is just effectively temporary energy storage that we can add into the system pretty easily to not have to completely change the infrastructure to handle these large loads. And it's done by adding in capacitor banks and stuff like that. So several years ago, I'd say several years ago, I think it's within the last 10 years actually, the Super Bowl was held in New Orleans. And Beyonce, I believe, was the halftime entertainer. And her stage show consumed more power than Entergy in New Orleans was ready for. And so it caused blackouts across the city. That could have been rectified by having more reactive power on standby to accommodate for this, right? Reactive power is largely used to prevent blackouts and prevent brownouts. So what it really does is it maintains voltage levels across the entire power grid by having this extra portion of temporary energy storage available. Okay, so it might seem like it's useless because it's just constantly transferring energy from the distribution center back to the distribution center, but it does have a very, very practical value, even though it isn't capable of performing mechanical work. All right. Apparent power will be the next thing that we talk about. Apparent power is the magnitude of the complex power. So it's simply the product of the RMS voltage and the RMS current. And it's typically denoted either as the magnitude of the complex power or just by S with no bar over it, letting us know that it's the magnitude of that vector or complex number. And because it's the magnitude of the complex power, it also has units of volt amperes. So typically speaking, if somebody's talking about, oh, this thing absorbs 7,500 VA, they're talking about the apparent power because they're not giving you any indication as to what the angle is, okay? Apparent power is a very important quantity because that's what power engineers design to, okay? So if any of you guys have ever tried to shop for something like a universal power supply or something like that, or done any design work for a small distribution system, you might see something on the box of a UPS that says it's rated for like 1,800 watts, 2,500 VA. So that means that 2,500 VA is the maximum apparent power that can be delivered, but it can only deliver 1,800 watts of average power, okay? That's also a very common thing that you'll see when you're trying to size a generator. It will give you two figures of merit. It'll give you the apparent power that can be supplied by the generator and the average power that can be supplied by the generator. So what apparent power really is it's kind of a worst case scenario for the amount of power that might be consumed by a given load. And I say it's the worst case scenario because it doesn't take into account any phase angle differences between the voltage and the current at all. It's simply the product of the magnitude of the voltage and the magnitude of the current. So it represents the maximum amount of power that that load could potentially absorb under the worst case conditions. And so that's why we design towards it, okay? All right. Our last thing here that we're going to talk about is what's called the power factor. So the power factor at which an electrical element or network operates at is a measure of the efficiency of power transmission to and from the network. Mathematically, I scrolled too far. There we go. Power factor is defined as the ratio of the average power divided by the apparent power, which comes out to be simply the cosine of theta v minus theta I, or you may alternatively see it as cosine of theta s, where theta s is what's called the power factor angle. Okay. Power factor ranges from -1 when a network is supplying apparent power at 100% efficiency to +1 when a network is absorbing apparent power at 100% efficiency. Okay, so when a load operates at a power factor less than a magnitude of 1, it means that the source is being required to generate more than the minimum volt amperes necessary to supply the required average power needs of the load. This typically means that the expense to the supplier is higher as more energy needs to be generated than is actually being consumed. So one way to think about some of these relationships, at least that I find helpful, average power is what we consume and what we are charged for. So when we receive an electricity bill, it's the average power that we're paying for. An electric utility generates apparent power, okay? And if our system isn't perfectly efficient, they are going to be generating more power than we as end users consume. If that value is too far off, we might get fined. So it costs an electric utility money in multiple ways to generate average power, or excuse me, apparent power, right? So it might be that they have to burn more coal to generate that apparent power. It might mean that they have to bring more hydroelectric plants online to generate that apparent power. It might mean that they have had to invest in infrastructure in solar and wind energy, and then the subsequent inverters that would convert that DC power to the AC apparent power that is supplied by the grid, all right? So if the amount of apparent power that they have to generate is too much larger than the amount of average power that we as an end user are consuming, they will fine us because we are costing them money to put that infrastructure in place to generate that apparent power, okay? We are going to talk about on Monday a concept called power factor correction. And what power factor correction is a way for an end user like us or a manufacturing plant or something like that to raise its power factor to an acceptable level so that they don't receive a fine from their utility, all right? Okay, so a few more things about power factors that I will actually test you on, so it's why I'm writing it down. Power factors are classified as leading or lagging. And this is where our talk about the concept of leading and lagging several lectures ago is finally going to pay off. So leading and lagging power factors depend on the sign of the power factor angle, theta s. When our angle is between 0 degrees and 180 degrees, or generally considered to be positive, we have a lagging power factor. And what that means is that the voltage leads the current, or alternatively, the current lags voltage. When our, and this is the one that we should really be looking at here. If our angle is negative, or we have 180 degrees is less than theta s is less than 0 degrees, we say that our power factor is leading, where the current leads the voltage. Okay, a power factor of 1, either plus or minus 1, and a power factor of 0 are not considered either leading or lagging. So a power factor of 1 means, by definition, that theta s is plus or minus 0. So theta s is either 0 or plus or minus 180 degrees, which means that everything is either in phase or perfectly out of phase. And so we are operating at 100% efficiency. A power factor of 0 means that theta s is either positive 90 degrees or negative 90 degrees, and we are operating at 0% efficiency, which means that we are supplying apparent power to a purely inductive or purely capacitive load. So I know that over the last 30 minutes or so, I have inundated you guys with a ton of different relationships. The next thing that I'm going to talk to you guys about is a very simple graphical tool that will help you figure out what the heck all these things are and not need to memorize 10 different equations, okay? So I want to talk now about what's called the power triangle. So for a generic load, Z is equal to R plus JX, where R and X are positive. The complex power absorbed by that load might look something like this. So here is our imaginary axis. Here is our real axis. And our complex power S is just a vector on that complex plane. The projection of S onto the real axis is our average power. The projection of S onto our imaginary axis is our reactive power. The length of our vector S is the apparent power, and the angle our complex power S forms with the real axis is our power factor angle. So all of our different relationships for complex power, average power, apparent power, reactive power, power factor, all that stuff are buried inside this one little diagram. Okay, so I think it's pretty dang neat. This guy comes from S is equal to V times I conjugate, which we know is P plus JQ, or S angle theta S. So I'm reinforcing this bit with the math here because I want to make it clear to you guys this is really the only mathematical operation that is required that you know how to do. Because you all use calculators. And you can choose whether the results of your calculators are given to you in rectangular form, which then inherently gives you average power and reactive power, or in polar form, which inherently gives you the apparent power and the power factor angle, okay? So you do not need to memorize all those equations by any shape or form. You just need to understand the relationships, which is conveniently summarized in this simple triangle. Okay. We can actually look at some or glean some extra information about the behavior of the load by looking at the power factor angle theta s, and recognizing that the angle theta s is the exact same thing as the angle of an impedance, right? So what I mean by that is that impedance is defined to be the ratio of phasor voltage to phasor current, which would be Vm angle theta V divided by Im angle theta I in polar form, or Vm over Im angle theta V minus theta I, which we know to happen to also be theta s, right? So from this, if theta s is equal to 0 degrees, our power factor has to be exactly 1.0, or our system is operating at 100% efficiency. And we know that the load is purely resistive, meaning that R is greater than, not 0 degrees, just greater than 0. And our reactance, X, is exactly equal to 0. If 0 degrees is less than theta s, is less than 90 degrees, our power factor is lagging. And the load is considered to be inductive, where R would be greater than 0 and X would be greater than 0. If theta s is exactly equal to 90 degrees, our power factor is 0. We're operating at 0% efficiency, and the load is purely inductive. Where R is equal to 0 and X is greater than 0. If negative 90 degrees is less than theta s is less than 0 degrees, our power factor is said to be leading. And the load is capacitive. Where R is greater than 0 and X is less than 0. And then finally, when theta s is equal to negative 90 degrees, our power factor is again exactly 0. And the load is purely capacitive. Meaning R is 0 and X is less than 0. All right, so I have literally half a page left of notes to cover on alternative relationships that we could use. This next bit that I want to talk about, you do not in any way, shape, or form have to memorize. You just might find them useful because it effectively eliminates some of the information that you may need to find to calculate the complex power. But before I get to that, I know that we've covered an awful bunch of stuff and I haven't given you guys a heck of a lot of opportunity to talk about things. So by all means, if any of this was confusing and you have a question, please allow me to try to answer it. So does anybody have anything they want to talk about before we move on here?
I mean, I don't think so. I would have to like look at a problem, but right now it all seems fairly straightforward and pretty much just definitions.
Yeah, that's really all it is. The math that's involved in doing this stuff isn't anything different than what you've done because it's just so solving for the RMS phasor quantities is the exact same thing as solving for the phasor quantities that you've previously done, except that now you have to divide by square root of 2, which your calculator can easily do. Beyond that, it's simply multiplying two numbers together and then getting the answer spit out at you in various forms. So I'm glad that at least one of you thinks it's fairly straightforward. All right. So the last thing that I want to talk about today before what I would like to do after I give you these relationships here is maybe take a look at your homework set and potentially work some of the problems with you guys as feedback. All right, so the last thing that we're going to talk about, let me see how much room I have. We'll start on this page, is what I'm going to call alternative relationships. And these relationships are literally just using Ohm's law to express things in slightly different ways. So just as a quick aside here, Ohm's law in the RMS phasor domain is this. So RMS phasor voltage is equal to RMS phasor current times the impedance. So it's the exact same thing as Ohm's law in the frequency domain, and the exact same thing as Ohm in the time domain. Ohm's law is Ohm's law, no matter what way we look at it, okay? So I can express my voltage as the product of current and impedance, or alternatively, I can say that my current is simply my voltage divided by, sorry, my impedance. So that shouldn't be an I, that should be a Z. All right, so complex power is defined to be V times I conjugate, or then we could say that it is I times Z times I conjugate. Do any of you guys remember from our review of complex numbers what happens when we multiply something by its complex conjugate? So let's say that I have complex number A, that is A angle theta A. The complex conjugate of A would be A angle negative theta A, right? So when I multiply A times A conjugate, I have A angle theta A times A angle negative theta A, which simply gives me the magnitude squared. So when I multiply my RMS phasor current I times the complex conjugate of my RMS phasor current I, I'm going to get the magnitude of my RMS phasor current squared times my impedance, which is going to look like IRMS squared times the magnitude of Z, the angle of theta Z, if I'm doing my impedance in polar form, or alternatively, it will look like IRMS squared times R plus J IRMS squared times X in my in rectangular form. So what's interesting, and the average power absorbed by a particular impedance. Now you really only need to figure out what the current flowing through the impedance is. And the current, it's just the magnitude of the current squared times the real part of the impedance is the average power. The magnitude of the impedance squared times the imaginary part of the impedance is the reactive power. So you're just getting these simple, easy relationships. I can do something similar with the other Ohm's law relationship that I've developed here. And so I can say that S is again simply V times I conjugate, which is going to look like V times V over Z conjugate, or VRMS squared divided by Z conjugate. Because when I take the conjugate of a fraction, it's the same as conjugating the numerator and the denominator. So if my impedance is in polar form, this is going to look like VRMS squared over the angle, excuse me, over the magnitude of Z with an angle of theta Z. And in rectangular form, I would have VRMS squared over the magnitude of Z squared times R plus J times VRMS squared over the magnitude of Z squared times X. Okay, those are my generic relationships. From these, for a purely resistive load, where R is greater than 0 and X is equal to 0, the complex power absorbed by a resistor is simply IRMS squared times R, or VRMS squared over R. So we can see that resistors absorb average, which I can't spell apparently, power. For a purely inductive load, again, R is equal to 0, X is greater than 0 for a purely inductive load. We would have SL is equal to J omega L times I RMS squared, or J VRMS squared over omega L. And so we can see that inductors absorb average power. And I say that because the complex power absorbed by an inductor will always be a positive quantity, right? Doesn't matter whether the voltage is positive or negative because we're squaring it, same with the current. So we're always going to have a positive quantity with regard to complex power absorbed by inductors. And finally, for a purely capacitive load, where R is equal to 0 and X is less than 0, we have SC is equal to negative J over I RMS squared divided by omega C, or alternatively, negative J omega C times V RMS squared. So capacitors always supply not average power, apparent reactive power. Gosh, I'm making mistakes left and right here. Reactive and reactive here. I apologize for that. All right, so that's the last of the relationships. So if you guys will humor me, I'd like to take a moment, or several moments really, and try to help you with your homework. So I'm looking at homework set number 23 right now. Problem 1, you are given several time domain voltages, and you are asked to find the average power absorbed by the resistor. So what I would do for problem 1 is get those time domain voltages to effective voltages, and then use the effective voltage to determine your average power, because it'll just be VRMS squared over R. So those guys are pretty straightforward. Problem number 2. Problem number 2 is pretty, I like it, and I get asked a reasonable amount of questions about it. So I'd like to go over that one with you guys if you're okay. So in problem number 2, we have the following circuit. So this is homework 23.2. We have a resistor. R, for me, is a 200 ohm resistor, so I'm just going to use the numbers that I'm given. We have an inductor, which has an impedance of J 280 ohms. And we have a capacitor, which has an impedance of negative J 305 ohms. We have a current source, IS, which is 2.9 angle 12 degrees amps. 2.9 angle 12 degrees amps. We have a voltage source over here that is 28 angle negative 180 degrees volts. And then we have an impedance here just called ZL. So it is just a generic load impedance. Okay. And what we are asked to do is find the following quantities. Thevenin voltage. So that would be VTH as a phasor quantity. Part B, we were asked to find Norton current. That would be I Norton, also a phasor quantity. The Thevenin impedance. That would be ZTH. Then for part D, we are asked in the problem statement, it says power absorbed by ZL. If ZL is equal to ZTH. Now, it does not explicitly say this in the problem statement at all. But when you go down to the little answer blocks and all that kind of stuff, it says specifically SZL is equal to something plus J something else volt amperes. So what it is asking about here is the complex power, okay? And that's what's going to trip, that portion is what trips up some students, and I'll explain why in a moment. And then for part E, we are asked to find the power, and again, this is representative of the complex power absorbed by ZL if ZL is equal to ZTH conjugate. Okay. All right. So, do any of you all remember how to find the Thevenin voltage with respect to a circuit element?
You create an open circuit where they're asking you to get it between those two terminals, and then you do either mesh analysis or nodal analysis to get the quantity you're looking for, VTH.
Yeah, so I would argue that you don't necessarily have to do nodal or mesh, but what you talked about open circuiting the element of interest is absolutely correct. So I'm super glad that at least one of you guys remembers that. If you remember that kind of thing, you're in fantastic shape for doing well in the final, okay? So to calculate our Thevenin voltage, I'm going to redraw our circuit with our ZL quantity taken out. So here is our, I think it was a 200 ohm resistor. Yep. So I took my ZL out. Here's 28 angle negative 180 degrees volts. Here's 2.9 angle 12 degrees amps. Here is my circuit. This will be my Thevenin voltage, VTH. So how might I go about determining that quantity, VTH?
You can do mesh analysis.
All right, so doing mesh analysis, I'm going to have exactly two meshes. I'm going to call this guy here mesh A, and this guy here mesh B. I am not going to have a third mesh around that bottom right-hand corner window pane because it's got an open circuit, so I know that there's actually no current flowing around in that loop. So I have a current source on the perimeter of my circuit. Right? So I could say, I'm going to draw a line here, that I know mesh current IB is equal to 2.9 angle 12 degrees amperes. And now I'm just going to write a Kirchhoff's voltage law equation around mesh A. So if I start here at the bottom left-hand corner, I'm going to have 200 plus J 280 ohms times IA sorry, I pressed a button with the side of my finger. Plus minus J 305 ohms times IA minus IB is equal to 0. And now I'll need to solve for what that quantity IA is, right? So I'm going to do that real quick here. So I'm going to have 200 plus J 280 minus J 305 IA is equal to, so I'm trying to make sure I'm getting my stuff over here, minus J 305 IB. IA is going to be negative J 305 IB divided by 200 plus J 280 minus J 305. Anybody see any issues with my algebra there?
I do not.
Okay. Throw it into my calculator. So I have minus fraction minus 305 I times 2.9 angle 12 divided by 200 plus 280 I minus 305 I get 4.388 angle negative 70.875. Amps. And I'm going to store that as variable A. So now that we know our two mesh currents, how does that help us determine VTH?
Wouldn't VTH be the 220 J ohm resistor times IA minus IB?
Wouldn't, okay, so the voltage VTH should be equal to 200 plus J280 times IA, or?
I don't agree with either of those things. So let me put some stuff here in red. I'm going to call this voltage VC. And I'm going to this voltage VL because it's a voltage drop over a capacitor and a voltage drop over an inductor. So the problem with the first statement where it was just the voltage drop over the 280 ohm inductor, that's only true if there is no voltage drop over the current source. And we have no reason by which to assume that. The 200 ohm resistor in series with the J280 ohm. Oh, actually, that is a good way. No, that still would be assuming that there's no voltage drop over the current source. So how I would approach this is I would write a Kirchhoff's voltage law loop equation around this loop, right? So what I would have, or what I would get in the end, would be that my Thevenin voltage is going to be 28 angle. Is it negative 180? Is that really what I got there? Hold on, sorry. I need to pull back up. Web work on my other computer. Sorry, that's negative 80, not negative 180. My apologies. I transposed everything else correctly though. Okay. And that 180 thing didn't show up in our calculation for IA at all. So I'm still pretty solid about that. All right. So we would have 28 angle negative 80 degrees volts minus VC minus VL. Is everybody okay with that? Or understand where that came from at a minimum?
Yes.
So that's just me doing KVL around that purple loop that I've drawn there and then reorganizing the equation kind of all in one go. So VC would be what?
Should be negative J305 times IB minus IA.
Absolutely right. And what is VL?
280 J times IA
Times negative IA.
Yes.
times negative IA.
Yeah, negative IA because that current mesh current IA is flowing into the negative polarity terminal. So we need to account for that. So I'm going to throw that in my calculator real quick here where I've stored IA as variable A. So while I'm at it, I'm going to store 2.9 angle 12 as variable B. And so I have 28 angle negative 80 plus negative 305 I times B minus A plus 280 I times negative A. And I get 905 with an angle, oh, excuse me, 905.326. With an angle of negative 71.156 degrees volts. Did anyone else get something similar?
I'm working on it right now. I got 875, so I'm trying to see where I could have messed up.
Let me make sure that I didn't also mess up here, because the answer that I'm getting is different than what WebWorks says is correct. 28 angle negative 80. Plus negative 305 I times B minus A plus 280 I times negative A.
I just redid it and I got your answer at 905 and negative 71.
All right, so .9, sorry. Let me make sure I didn't calculate IA wrong real quick, just because it WebWork, when I check the answers for the numbers that I have, it's telling me that it should be 850 with an angle of 109. And so if we're getting the exact same results.
Dr. Hartman, were you not meant to subtract VC and VL instead of add them in, or did that take care of itself based on the signs of IA and the negative J?
Okay, so I shouldn't be adding VC and VL from 28 angle negative 80. I should be subtracting because of the polarities of the voltage, right?
Right.
So if I do KVL, I would have 28 angle negative 80 degrees is equal to VC plus VL plus VTH. So that's where those negative signs come from. VC, oh, whoa, I see what you're saying there. Okay.
Yeah, whenever
Yeah.
you did that, you added them. I got 850 with an angle of 109.
Okay. Which is exactly what you're supposed to get. Thank you. Okay, so I just made a dumb math mistake there. I added them instead of subtracting them. Thank you so much.
No problem.
We didn't screw up IA. Fantastic. All right. Let me change the sign on those guys real quick. Thank you very much for noticing that. $850.036 with an angle of 109.424. All right. How do we determine the Norton current? Or let me ask a slightly different question. We need to find now the Thevenin impedance and the Norton current, but we really only need one of those quantities to find the other, since we know the Thevenin voltage. So if we were to try to find the Norton current, what we would do is we would short out that impedance ZL and find the current flowing through that impedance ZL. That being said, that would require us to set up a nodal analysis system where we would have two, I guess no, the only unknown voltage would be the voltage drop across the current source. So that would be one way to potentially do it. We'd have to do nodal analysis to figure out what that voltage is, and then do Kirchhoff's current law at the node where the resistor and the inductor are connected to figure out what the Norton current is. So it would be two steps there. Or we would wind up doing mesh analysis where there are 3 meshes that we'd have to take care of. Our other option is finding the Thevenin impedance directly and then using that to calculate the Norton current. And to me, that seems like a much easier thing to do. So let's find the Thevenin impedance directly here. Right? So our Thevenin impedance, what we're looking at is a 200 ohm resistor. Our capacitor, which was minus J305. Our inductor, which was J280. Here's a terminal. Here's terminal. Our voltage source is turned off. And our current source is also turned off. So this is our equivalent circuit. So what does ZTH look like?
That would be the J305 in series with the J280, and those two are in parallel with the 200 ohm.
Yep, so 200 ohms times negative J305 plus J280 divided by 200 minus J305 plus J280, whatever that comes out to be. And then kind of jumping ahead here because I didn't realize we were this close to being at the end of class. I Norton would be VTH divided by ZTH, right? So for parts D and E, and I'll just kind of talk you through this real quick under the assumption that you've gotten parts A, B, and C correct at this point. We want the power absorbed if ZL is equal to ZTH. So we know what VTH is. We know what ZTH is. And we now have ZL is equal to ZTH like this. What we need is VL and IL, but because we're calculating complex power, we need to be looking at the RMS phasor voltage and the RMS phasor current. So the error that I see most students make right here is using VTH instead of using the RMS version of VTH. This is the one that needs to be used. From this point, then, VL is simply VTH over 2, and IL simply VTH over twice ZTH. And then we have enough information to calculate the complex power as SL would be VL IL conjugate. So that's how you would take care of part D. For part E, So we're going to be working with the RMS Thevenin voltage again. ZTH. ZTH conjugate here. Still looking for VL. And we're still looking for IL. Well, now we see that VL is going to be VTH times VTH conjugate over VTH plus ZTH conjugate. IL would be VTH over VTH plus ZTH conjugate. And then we take the complex power from there. So a very common mistake, and it's, I don't even really want to call it a mistake, but a thing that students seem to miss when they're doing these homework sets. If you're calculating anything that you will use complex power to get, you need to make sure that you're using the RMS values. You can tell whether or not you were given the RMS values of voltage and current if the units are expressed as volts RMS and amps RMS. If not, you were just given the phasor voltages, and so you need to convert simply by dividing by square root of 2. Okay, so I just want to make that very, very clear, because if you don't recognize that, you could be working the problem perfectly correct, except for that small subtle difference, and find yourself getting the wrong answer and get frustrated and all that kind of good stuff. All right, I ran a couple of minutes over, so I apologize for that. On Monday's class, we will cover power factor correction. That is the last topic. Should take maybe 30 to 45 minutes total. So if you have any review type questions that you would like to address on Monday afternoon, I'd be happy to answer them then. And then I believe we'll have the official review on Tuesday. I do want to let you guys know, my grandfather passed away yesterday, so I am going to have to be doing some traveling to attend his funeral. I'm not sure when it is going to be yet. So if I have to reschedule a review session or something like that, I'd like for you guys to work with me, but I want to make absolutely sure that we do get a review session in before the exam. So I'll work with you as best I can to get that where it will serve the most amount of people. All right, any other questions or anything before we wrap up for the day?
I don't think so.
All right, well, I will hopefully see you guys on Monday. Like I said, it depends on when the funeral is and all that kind of good stuff, but yeah, I'll see you guys sometime next week.